Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, Professor of Mathematics at Cosumnes River College in Sacramento, California. This video is dedicated for those students who are in college algebra or perhaps a pre-calculus course. To be honest with you though, I do have a different video for something like this for a pre-calculus student, but this is usually for those who've just come out of intermediate algebra or algebra 2 from high school or something like that. And we are just going to go over simplifying compound rational expressions because they become ultimately very important as you move forward in mathematics, especially if you're in the STEM track. So what is a compound rational expression? Well, a compound rational expression, also known as a complex rational expression, is any rational expression containing other rational expressions. That is, a compound rational expression has the form p of x over q of x, where at least one of p over q is basically a fraction. They both could be fractions, but at least one of them is a fraction. For purposes of reference, these rational expressions, p and q, will be called sub-rational expressions. I will call them that quite often just because it helps us identify what we're talking about. So here's an example of a compound rational expression. It's a fraction, a major fraction here, this guy right here, and it contains fractions. You can see fractions all over the place in this. So we are going to go ahead and figure out how to simplify these. And because this is a review, it's not that we're going to go ahead and find out how to do that. We're actually going to recall how to do that. And the how-to goes as follows. Somebody gives you a complex or a compound rational expression and you're asked to simplify. The first thing you do is factor all denominators. So that means go through all the sub-rational expressions and factor all of their denominators because that helps you identify the LCD, which we're going to need in a moment. And then step 2, identify the LCD. Well, there we go. That's the thing I was just mentioning. So identifying the LCD of all the sub-rational expressions within the compound rational expression, and you're going to write this down. Step 3, you're going to multiply the numerator and denominator of the major rational expression, the main one, by the LCD, and then simplify. That's it. That's really all you have to do. Some people have been taught other ways to do this, but I'm telling you, this how-to, this way to do it that I'm showing you here is hands down the best way to do it because it covers all cases. If you've been taught something else, it only covers a certain type of compound rational expression. This, on the other hand, covers all types of compound rational expressions. So let's go ahead and start with this compound rational expression. And I like to start with this because a lot of people see this and they think it's not a compound rational expression because they don't see fractions within this fraction. However, there are fractions within this fraction. In fact, you know by the laws of exponents that anytime that you have a negative exponent on an expression, you could rewrite that expression as 1 over. Let me write that law of exponents down. So b to the negative n is equal to 1 over b to the positive n power. That's what we're going to use here. Another thing I need to note is when you're doing this, a major mistake that usually people who are kind of shaky with their algebra that they make is that they apply the negative exponent not only to what it's touching, which is that guy right there in this case, but they also end up inappropriately applying it to what it's not touching. So that -1 as an exponent is only touching the x. It's not attached to the 3. So when we apply this law of exponents, we're only doing so with expressions where the negative exponent is touching the base. In this case, the 3 is not touching that -1 exponent. That's 3 to the first, attached to an x to the negative first. So let's go ahead and rewrite this expression. So this is equal to 3 over x minus 3 over y, all being divided by 1 over y squared minus 1 over x squared. Again, notice the stuff that dropped down to denominators, that stuff had negative exponents. Another major mistake that I'll often see students make when they have kind of shaky algebra skills. So I'm going to say this is not equal to this, but this is what a lot of people do. They write this as 3 minus 3, and they'll drop that x downstairs and they'll drop that y downstairs. And then I don't know how they do the rest of this, to be very honest with you. It's so wrong. But this is not what it turns into. So this statement right here is actually by itself just a 3 over x. This statement by itself is a 3 over y. It is not 3 minus 3 over x times something minus y times something. That is not true. That's just something that I've seen people do in the past. It's pretty terrible, so I'm going to get it off the screen because it completely does not make sense. Now at this point, once you have your compound rational expression written this way, where it's a fraction containing fractions, now you're going to go ahead and identify the LCD of all these minor sub-fractions. That's what I was calling earlier the sub-rational expressions. They're the minor fractions is what I would normally call them. And you can see the first one here requires us, our LCD, to have an x. So off to the side, I'm going to go ahead and write that our LCD at least has an x. And then I go ahead and go to the next one. And by one, I mean the next term in the numerator. The next term in the numerator is 3 over y, and so therefore the LCD, or the contribution to the LCD from that term, is going to be the y. So I'll go ahead and slide over here and say that we also need a y. Now I'll go back over here. Notice the 1 over y squared in the denominator. The y squared tells us that we need a y squared for our LCD, so I'm going to actually add a power to this y here. Likewise, if you look at the final term, or the final sub-fraction, if you will, this guy right here, we need an x squared for our LCD to represent that denominator. So moving over and plugging in a 2 for our power there. In general, kind of the main idea with LCDs is that you just look for each factor that exists and you take the highest power version of each factor. So looking through all these denominators, the x, the y squared, the x squared, you take the highest powered version of each factor. So for x, the highest power that you see in that grouping is a second power. For y, the highest power in that group of highlights is a second power. Now, once you've identified the LCD, all you're going to do is multiply this fraction that we've created by 1, but it's a very special version of 1. It's going to be the LCD divided by the LCD. Remember, you do not want to change the value of an expression you've been handed. What you want to do is rewrite that expression as an equivalent fraction. And the only way you can do that is basically by multiplying by 1 the entire time. And the very special version of 1 that we're going to multiply by is x squared y squared over x squared y squared. Basically, LCD divided by LCD. When you distribute this expression through to both terms in the numerator, from your prerequisite algebra, you know what happens. In the first term, the x will cancel downstairs with 1 power of x in the numerator, and in the second term, y will cancel with 1 power of y in the numerator. Likewise, in the denominator, we'll distribute this through. Very common that I will see people forget to distribute or multiply the denominator by the LCD as well. That is a requirement, otherwise things go haywire. And notice after distribution and after canceling like factors, you end up with a clean, proper fraction here where you don't have fractions within this fraction. However, you do have to factor. After you're done distributing the LCD to both numerator and denominator, it is very often the case that you have a little bit of factoring to do to simplify this expression. Notice both terms in the numerator have a 3, an x, and a y in common. So that's the GCF in the numerator. I'll just factor that out. And in the denominator, you have a difference of squares. Again, a prerequisite algebra skill. So that's going to be x minus y times x plus y. And if you thought you were done here, you're incorrect. That factor of y minus x in the numerator, that guy right there, you can actually change that into an x minus y to match this guy in the denominator. The way you're going to do that is to factor off a -1 like you would in Algebra 1. So factoring off a -1 off of the y minus x factor, I'll pull that out into the front of that 3xy, and I'm left with now the x will be positive and the y will be negative when you do that. Downstairs, we still have an x minus y, and we have an x plus y. You can easily see that the x minus y factors will cancel beautifully. Remember, only factors cancel, not terms. That's just something from your algebra course. Now that we've done that, we are ready to write our answer as a -3xy divided by x plus y. And that is completely done. That is a simplified version of the original statement, and in fact, a much better version of this original expression. Now, as I went through this, I tried to mention the pitfalls that I commonly see happen in an algebra class, an Algebra 1 course, an Algebra 2 course. By the time you're in college algebra, you should not be making those mistakes. If you do make those mistakes, recognize them as quickly as possible, write them down, write the mistakes you make down so that you know you're prone to that mistake, and then dedicate yourself to really ferreting out and finding out when you make those mistakes and not making those mistakes. Try your best to not make that style of mistake. As our second example here, we're going to take a look at a compound rational expression involving functions you may not even know. If you're in a traditional college algebra class, you likely have not met trigonometry yet. However, you don't really need to know trigonometry to simplify a compound rational expression. This picture that you're looking at right now, and I like to call it a picture just because that's really what all mathematical expressions are. They're just pictures full of symbols. This is essentially a 1 over something, I'll call it a happy face, plus 1, and then plus, and then we can finish this out. So you can see that I'm just trading out that unknown function, which is a sine function from trigonometry, for just a symbol, because that's really what it is. And sorry that bottom one right there looks like he's smoking a cigar. My pen went kind of wacky. But the way that you would simplify this compound rational expression is exactly the same as how you would simplify this compound rational expression. Now, rather than dealing with the happy face notation, even though it's a cool notation, I'm going to go ahead and stick with the original trig functions, despite the fact that you may not know what they are. I want to convince you that you could still do the mathematics without knowing anything about trigonometry. I'll start by mentioning the LCD. So you look through all of these subfractions here, each one of them I'm highlighting separately, and you write down their denominators, the highest power of each denominator. For example, in this first fraction, I know my LCD will require to have a sine of that theta. That's a Greek letter theta, theta, plus 1. The second fraction requires us to have a sine of theta minus 1 in our LCD. So I'll write that in here. And I'm using brackets there because I don't like to have parentheses and parentheses. So I just like to have different container symbols, that's all. And then the first fraction in the denominator requires us to have a sine of theta minus 1, but our LCD already has a sine of theta minus 1. And then the second fraction in the denominator requires that our LCD has a sine of theta plus 1. However, again, our LCD already has a sine of theta plus 1. What am I going to do with that LCD? I'm going to multiply both numerator and denominator of this compound fraction by that LCD. Very important thing when you multiply a fraction by the LCD, or you basically do anything like what we're doing here, make sure you use grouping symbols liberally. That is, I want to multiply that entire numerator by the LCD, which is sine of theta plus 1, sine of theta minus 1. And at the very same time, I want to multiply that denominator by that LCD as well. Again, very, very important that you use grouping symbols on this master fraction, if you will. And also that you multiply both numerator and denominator of that master fraction by the LCD. If you only multiply the numerator by the LCD, you are not multiplying by the number 1, and you're actually changing the value of this fraction. But if you multiply by LCD over LCD, which is what we're doing here, then you're multiplying this fraction by the number 1. So you're not changing its value, you're just changing its look. Distributing that LCD across both terms in the numerator, you'll see the very first term, the sine of theta plus 1 will cancel, and you'll be left with a sine of theta minus 1. Plus, the second term in the numerator, the sine of theta minus 1 will cancel with the sine of theta minus 1, and you're left with a sine of theta plus 1. Now you may wonder, why is he writing a parenthesis there? It's because of what's going to happen in the denominator. I just want you to get in the habit of using grouping symbols liberally. In the denominator, be very, very careful. I'm going to grab this guy and distribute it to each of the terms here in the denominator. The very first term, the sine of theta minus 1s cancel beautifully, and you're left with a sine of theta plus 1. In the second term, the sine of theta plus 1s cancel beautifully, but remember there was a minus sign hanging out front, so you're going to be left with a sine of theta minus 1, and just remember you're subtracting off that entire sine of theta minus 1. If you do not use grouping symbols, you will have division by 0 here, and it will be wrong. So remember to use grouping symbols. This is just a reminder from your Algebra 1 days. So if you have a problem with that, or if that's something that you know is an Achilles heel for you, or something that you struggle with, remember to write that down on maybe the front page of your notebook. List all the mistakes that you're prone to, and just tell yourself, do not make these mistakes. Every time you do a homework problem, look at those mistakes, see if you're making any of them. Well, at this point, it's just combining like terms. In the numerator, we have a sine of theta plus a sine of theta, which is 2 sine of theta, and we have a negative 1 plus 1, so they cancel beautifully. So the numerator is just 2 sine of theta. In the denominator, we have a sine of theta minus a sine of theta, so the sine of theta is canceled, and we have a 1 minus a negative 1, or in other words, 1 plus 1, which is 2. The 2's cancel beautifully, and you're left with the sine of theta. Even though you don't know what that function is, you know the end picture is just sine of theta, and that's it. So this is a really nicely compressed version of the original statement. Remember, the original statement was this guy right here. And if you look at that, that's a pretty messy original statement. And that's just a fancy way of saying sine of theta. Now I'm sort of hand waving here a little bit. If you're an advanced student, or if you're pretty on top of your game, you should be wary of domain issues. In the original problem, there are some domain issues that don't exist in the final expression. For example, in the original expression they handed us, sine of theta cannot be 1, because if it were, we'd have division by 0 in that second fraction in the numerator. Also, sine of theta can't be negative 1, because again, if it were, then we'd have division by 0 in the first fraction of the numerator. However, you would never know that if somebody worked on this problem to simplify it and got it down to this beautiful sine of theta. You would never know that there's some type of restriction. So that's a heads up for the A students. Please be aware that's something you're going to have to watch out for as you move through mathematics. But for right now, it's not a big deal for us. This very last example in this video really showcases the strength of using a method that I don't use. I know I'm supposed to say like use my method and my method only, but that's kind of not realistic. I really applaud students who are willing to be creative and use other methods when other methods can apply. Let me just showcase what I mean. If you use my method here, my recommendation is, okay, if you see this, you notice this is a fraction, this guy right here, divided by a fraction. And according to what I'm telling you to do, you would first factor all denominators, And I'll just move over to the side for that. And then you would look at all the denominators of the minor fractions, these guys right here, and you would write down the LCD. Remember, you're taking the highest powered version of each factor. So in blue off to the side, I'll just write down the LCD. Notice that my LCD has an x plus 2 because, well, that top fraction has an x plus 2 in its denominator. It has an x plus 3 because both of those minor fractions have an x plus 3 in their denominators. And then finally, it has a 5 raised to the x plus 3. And that's because this denominator has a 5 raised to the x, but the second denominator, the one in the actual denominator there, has a higher power of that 5 to the x. It's 5 to the x plus some more. So remember, when you find the LCD, you're always taking the highest powered version. Now again, following what I had recommended, and I kind of still recommend, you would then multiply both numerator and denominator of this bad boy right here by that blue LCD. Let's go ahead and do that. So remember, I'm multiplying both numerator and denominator by the LCD. And when I say both numerator and denominator, I mean of the overall large fraction. You see in the numerator, the x plus 2's cancel beautifully, the x plus 3's cancel beautifully. And then by the law of exponents, we have a law of exponents. I'll write it off the side in green. If you have a base to the m power divided by the same base to a different power, that division will be the base to the m minus n power. Well, we have a base of 5 to the x plus 3 divided by 5 to the x. Well, that'd be 5 to the x plus 3 minus x, or in other words, 5 to the third. So let me write that result down below, and let me showcase the cancellation that actually occurred. 5 to the x goes into 5 to the x here, and you're left with 5 to the third. In the denominator, the x plus 3's cancel beautifully, and the 5 to the x plus 3's cancel beautifully. And you're just left with x plus 2 times 4 times 9 to the x minus 1. And at this point, you're done with all the compound fraction business, and now you just have to kind of reduce this or simplify this down. You know that 2 goes into 4 twice, so you could technically write this as, well, 5 to the third is 125 times 3 to the x plus 2 divided by 9 to the x minus 1 times the quantity x plus 2. However, there's more that you can do here. Another law of exponents that you should always remember is b to the m plus n is the same thing as b to the m times b to the n. That is, this business right here can be written as 3 to the x times 3 squared, and this business right here can be written as 9 to the x times 9 to the negative first. Let's go ahead and do that. Now, once you get down to this business right here, you can start kind of manipulating even further. You know that 3 squared is 9. You know that this right here can be moved upstairs, right? 9 to the negative first can be moved to the top as 9 to the first. So I'll go ahead and do that right now. Now you get down to this point right here, and you think you're pretty much done, right? 9 times 9, you can figure that out. And then 125, you could probably do that as well. But there's something hidden here. I'm really trying to sneak into this problem a lot of review if you're in college algebra. You should know that 9 is 3 squared. So we're really looking at 3 squared to the x when you're looking at 9 to the x. And by another law of exponents, this is going to be 3 to the 2 times x power. So let's go ahead and replace that 9 to the x in the denominator with 3 to the 2x power. Now that's compressed down quite a bit. I also obviously multiply 9 and 9 together, but we still have a law of exponents we can use here. Remember that, I think it was way up here, b to the m over b to the n is b to the m minus n. Since you've had experience with algebra for so long, I'm actually not going to belabor this issue. The reality is that if you have 3 raised to the x power in the numerator and raised to 2x in the denominator, the powers of 3 to the x will cancel and you'll end up with a single power of 3 to the x downstairs. Another way you can think about that is the following. You could easily see that 3 to the 2x is the same thing as 3 to the x times 3 to the x, and this allows you to cancel one of those 3 to the x's there. In the end, you get the following. That is the simplified version of the original statement that was handed to us, that really messy statement up there. It took a lot of work to get there for such a simple problem, or a simple process, I should say. But this is the way that you would do it if you were following my advice pretty much religiously. If you followed my advice and just always multiplied both numerator and denominator by the LCD, you would get to this point eventually. There is another way to do this. It's not a way that I would always recommend, but again, my A students are the ones who can kind of pivot when a problem's slightly different and they know a better technique. So a better technique for this is to recognize what a division really truly is. Remember, you were handed 2 times 3 to the x plus 2 power divided by, and then I factor that out, right? So x plus 2 times x plus 3 times 5 to the x, that's the numerator of this original fraction. And that is being divided by, so I'm going to say divided by here. Old school arithmetic symbol, right? It's being divided by 4 times 9 raised to the x minus 1 all over x plus 3 times 5 raised to the x plus 3. If you do it this way, it's actually kind of a faster sort of way of doing it. Remember, dividing by something is the same thing as multiplying by its reciprocal. So you could have written this as this. And at this point, you can start canceling. And this is exactly where you would have arrived at this step, or second step right here. So I don't want to say it's any faster, honestly. It's just a different way of doing it. It involves not finding the LCD. So you can see the x plus 3 is canceled. Let's see, the 5 to the x goes into 5 to the x plus 3, 5 to the third times. 2 goes into 4 twice. So it does clean up somewhat quickly, but you still have all that extra work with 3 to the x plus 2 being 3 to the x times 3 to the second, and 9 to the x minus 1 being 9 to the x times 9 to the negative first, and going through all that. So you still do have a lot of extra work in this problem, but I just want to showcase that a good student has the ability to pivot and choose a good method for the problem itself. The method that I teach always works. The method that you see here only works, this method that I don't teach, this method only works if the fraction that you've been handed doesn't have addition or subtraction. I'm not going to say anything else about that because I'm not teaching an Algebra 1 course, I'm teaching a college algebra course. So let's go ahead and call it quits for this video. I will see you in the next video.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.